All right, welcome to section 7.2, a little throwback Thursday for y'all. So we are going to be talking here about Riemann sums and partitioning to sort of make those rectangles, but make them in different ways and calling them by a different name. So the first thing that we're going to talk about is the norm of partition. And you've got this wonderful like P with absolute value looking symbols around it. And that's just the symbol for the norm of partition. What the norm of partition is just the largest interval within the partition. So when we're talking about partitioning, we're saying that in all the problems that we've dealt with, we've talked about making rectangles that are equal width. Now we're going to say, well, what if we divvy that up in a different way? That's how we're partitioning it. So we're going to use the equation y equals x squared plus 2 on the interval 1 to 4. And our partition is going to be cutting it off at 1, 1.7, 2.3, 3.5, and 4. So if I look at each of these intervals, let's change that width. If I look at this interval, that is a difference of 0.7. Here I have 0.6. Here I have 1.2. And here I have 0.5. So the norm of partition is just the largest interval. So that would be 1.2. Next, I want to use the idea of drawing rectangles to estimate the area under the curve by using a left-hand endpoint. So we've talked in 7.1 about circumscribed and inscribed. You're not really going to see those as often. What you're going to see is something like left-hand or right-hand Riemann sums or Riemann sums. So the first thing I'm going to do is just give a quick sketch of what this graph looks like. X squared plus 2, so I've got a parabola starting at 2. And I'm partitioning this at 1, at 1.7, at 2.3, at 3.5, and at 4. What makes it a left-hand rectangle or left-hand Riemann sum is the fact that the height of this rectangle, or the height of each of these rectangles, is going to be given by the leftmost point in that rectangle. So then when I'm drawing this, I can see all of these rectangles. And you can also see right away this is going to be an underestimate because I'm not going to be counting all of this little space underneath the curve. So if I'm finding the area here, I'm looking at each rectangle and again just doing base times height, but the base is going to be changing for each one. So I'm going to have 0.7 times the height here is given by doing 1 and substituting it into this equation. Remember that this is the equation f of x equals x squared plus 2. And if I substitute 1 into that, I get 3. So I have 0.7 times 3. Substituting 1.7 in. If you substitute 1.7 in here, we get 4.89. So I'm going to have 0.6 times 4.89. Plus, my next partition is going to be 1.2. And I want to look at the height at that point. So substituting 1.2 in, I get 7.29. So I have 1.2 times 7.29. Our last partition only has a base of 0.5. And substituting that 3.5 in, we're going to have a height of 14.25. So I have 0.5 times 14.25. Very dry and nothing that's particularly new to us. We've dealt with finding these rectangles already. The only thing that's different here is just that that base isn't constant, it's changing. Multiply this all together, you get 20.907. All right, so then the next thing, oh gosh, we went way too far in this. I wanted to go all the way to section 7.5. I was excited. That doesn't even exist, 7.4 I meant. You and a companion are driving along a twisty stretch of dirt road in a car whose speedometer works, but odometer is broken. To find out how long this particular stretch of road is, you record the car's velocity at 10-second intervals with the results shown in the table below. Estimate the length of the road. So, just your everyday, day-to-day that we're going to be dealing with. We have a broken odometer. We want to find out how long is this road, and we can use some calculus to estimate that. So looking at these time intervals that we have, we're going from 0 to 60. Notice that these are divvied out correctly, so we don't have to worry about partitioning it in the way that we did here. They're divvied out by tens. The first thing we're going to do is a left endpoint, but we're only going to do 6 subintervals for each of these, just a slight change. So if I'm going to be using a left endpoint, something to realize, and I think the graph is really helpful for this, is when I'm dealing with a left endpoint, I'm talking about the leftmost point being the height. And what that means is that endpoint 4 was not actually used at all in our equation. Because a left endpoint, that 4, that height at 4, isn't part of any of that rectangle. If I'm dealing with a right-handed rectangle or right-handed Riemann sum, that means that all of these points for these rectangles are going to move to the right. So I wouldn't need the leftmost. Using it from this table, something to keep in mind is that this is really like my x or my t axis, and this is really like my y axis. So when I'm looking at this first interval, this rectangle has a base of 10, and its height, we're talking about a left endpoint, so its height is whatever's on the left, 0. We'll do the next rectangle, and you want every span of 10. So here, a distance of 10. So we have 10 times the left height, 44, plus 10 times 15, and we'll just continue this on 10 times 35, 10 times, ooh, that's not a 3, that wasn't a number, plus 10 times 44. Now notice I'm not going to have one that's 10 times 35. Here are my 6 intervals, left endpoints because I'm using that left y value and not the right-handed one. Multiply this all together, we get 1,680, and we're working in feet. Now your right endpoint is going to be very similar to this. We're still looking at those same intervals, so my base for all of them is still going to be 10. The only difference here is that I'm not concerned with the left y value, I'm concerned with the right y value. So we're starting with 10 times 44, and we'll just be continuing throughout this list for each one of these rectangles. So I have 44, then 15, 35, 30, 44, and my last one is going to be at 35. Again, I need this last one because it is a right endpoint. So this rectangle has a base of 10, and its height would be given from the rightmost point. Multiply this all together, I get 2,030 feet. So here we can see we have an underestimate and an overestimate. Our actual would be somewhere between these two. All right, so then we also have what's called the trapezoidal rule. The trapezoidal rule is when we take the average of the left endpoint and the right endpoint approximation. So this is a rule that sort of gets us around doing the left endpoint and right endpoint approximation, but you can always do the left Riemann sum, then the right Riemann sum, and take the average. The trapezoidal rule is just then saying we could take the area of all these trapezoids, your area formula being 1/2 the height times the sum of the bases. And one thing really important to realize here is this trapezoid is essentially turned on its side, and it's not a regular trapezoid. So the height is really the distance between your parallel sides. So your height is really along the x-axis. And base 1 and base 2 are really your two y values, because that's going to be giving you how high that trapezoid is going, but not exactly height distance between the bases. All right, so let's do an example of that. The following table shows the speed of a runner taken every 1/2 of a second. Estimate the distance that the runner went. Use the trapezoidal rule, and we're actually going to be doing 4 subintervals of equal length. So I'm going to do this essentially the same way that I would start by doing a rectangle. I'm looking at this sort of distance here. My trapezoid rule is 1/2 the distance between the bases. So the distance between the bases here would be 1/2 or 0.5. And then you want the sum of the bases. The bases again are your y values. So here was my x or my t. here's my y. And y is giving me the length of the base. So I'm going to have 0 plus 6.2. My next one, sort of like doing a rectangle, I would have this interval. So I'm going to once again have 1/2 times 1/2, and then 6.2 plus 10.8. And continuing that 1/2 times 1/2, I'll have 10.8 and 14.9. And lastly, 1/2 times 1/2, and I have 14.9 plus 18.1. One thing that you can notice is a little bit different from this to a left or a right-hand Riemann sum is we do use all of the y values, but some of them are used more than once because they are both the end of one trapezoid and the start of another trapezoid. Multiply, add, get all that, you get 20.475 feet. And then the last thing we're going to talk about is a midpoint Riemann sum. So a left Riemann sum is going and taking your point furthest to the left. The right Riemann sum is going and taking the point all the way to the right. The midpoint Riemann sum is saying we're going to take the middle point between two. We're only going to have 3 equal subintervals here. So the first one, if we need the point that's in the middle, we're going to be talking about taking this whole 3 sort of cells in this table in order to get that first rectangle. So if I'm looking at this, it is a rectangle. So the base, I'm going from 0 to 1, base is 1, times the height. Now, if it was a left hand, I would use 0. If it was a right hand, I would use 10.8. For a midpoint, I'm using that middle number, 6.2. Not really revolutionary there, midpoint, taking the middle. My next interval is going to be here. So again, I need a span of 3 because I need that middle. My change in x is 1 there, and my height is 10.8. And last, looking at this last interval, 1 times that midpoint, 14.9. Multiply that all together, we get 31.9 feet. And you'll see here, you get pretty far off answers, especially using that midpoint, depending on how this graph may look. But your trapezoidal usually going to give you a better approximation because you're averaging the left and right sum. So you're minimizing the amount of over or underestimate for each one of those intervals. All right, so that's all that we're covering so far in section 7.2, Riemann sums. Just keep in mind, we're not going to necessarily talk about circumscribed or inscribed as much now. We're going to talk about something like left-handed, right-handed. And then we'll get into the rest of 7.2, which is just, some more fun calculus, less graphical.